Hey there everyone, welcome to video 3 of apportionment, setting up your project. It says day 2 here because when I cover this in class, this would now be day 2's material. However, this is the third video talking about apportionment material. So the point of this video is now to get back to some calculus. So the last couple of videos seem like kind of a strange left turn into nowhere, right? Like what are we doing talking about presidential primaries and apportionment theory? So the goal of these slides is now to define the notion of delegate bias, which is defined in terms of a double integral, it turns out. So we can connect this material back to chapter 15. So first, just a bit of calculus. So if f of xy is a two-variable function and D is a region in the xy plane, the average value of the function on that region is defined like this. So you take the integral of the function over the region, and then outside you divide by the area of that region. This is the average value of a function on a region, and the image you should have in your mind is something like this. The average value of a function is the height at which you set this water so that if you were to slice the tops of these hills off, the volume you slice off is precisely the amount you would need to fill in the valleys. Okay, so let me say that one more time. The average value of a function is the height at which you set this water, so there's an equal amount of volume above that level, that water level, as there is below. So that if you were to slice off the tops of these mountains here, you would then fill in exactly, be able to fill in exactly these valleys to get an even flat surface. That's the idea of an average value. So you're kind of cutting the function in the middle, which is what an average should be doing, right? So it's almost like a median value actually, but the term people use is average value. Okay, so you set the water level so there's an equal amount of volume above as there is sort of empty space, empty volume, negative volume below. Okay, so let me now remind you of the images from last time. Here's Hamilton's method with 3 candidates and 8 delegates. We looked at this last time, but I need this to think about my integral in this video. And then recall that this triangle is divided into 6 regions according to the 6 possible rankings. So down here actually is where we will focus our attention. We're going to assume that candidate 1 is the leader and candidate 3 is the loser. And then candidate 2 comes in second. So we'll be living down here for the rest of this project. So in terms of this picture here, we'd slice off this bottom 6th. So the hexagon 521 is relevant. The hexagon 215 is no longer relevant because candidate 1 is not in first place here. Here's the NIE method with 12 delegates, and I've zoomed in on the bottom 6th. So here is the part of that triangle where candidate 1 is in the lead and candidate 3 is last place. So this little arrow guy here with 831, that's relevant here. And here's the SUQ method with, again, 3 candidates and 12 delegates, and you can see these little diamonds being formed. As we discussed last time, that's sort of the canonical shape of the SUQ method. And like this sawtooth thing looking here goes to 930. This sawtooth thing here goes to 840. So all this stuff here is flowing to this point down here. This tiny little triangle slice right here is flowing to the point 921, it turns out. This line here, again, this is the tie line between where candidates 2 and 3 swap places. So along this line, see 1, 1, 4, 4, candidates 2 and 3 are tied. So if you move across that line, suddenly you'd have like an 8, 1, 3 or something. You'd be swapping the places of those last 2 candidates. Okay, so now let me define some last bit of vocabulary that we need that we can connect to the calculus. So given an apportionment for a given election, a candidate's deviation from quota is that candidate's apportionment value minus the candidate's quota. So it's what you actually get, right, your apportionment, minus what the raw math says you should get, right? The quota is what the raw math says you should get. You know, I'm entitled to 9.3478 delegates or whatever, right? So it's like, it's the distance or the difference, however you want to say it, right, between what you actually get and what the math says you should get, the raw math. Okay, so here's just an example. So here's D equals 27 delegates. Let's calculate each candidate's deviation from quota for this election for all 3 of our methods. So just for the sake of time here, I'm not going to go over to the calculator, but you should go over to the Hamilton's method calculator yourself that we looked at in a previous video to calculate the apportionments here if you're not comfortable with these methods. So I went to that calculator and it told me, first of all, the quotas are these. So if you want to calculate deviation from quota for a given candidate, you of course must know that candidate's quota. So here they are. Now the Hamilton apportionment, it turns out, is 12, 7, 5, 3. So again, you could just ask the calculator for these things, but you can sort of see that happening here. If you round everybody down, 12, 6, 4, 3. If you do that and hand out the 12, 6, 4, 3, you will be 3 delegates short of the 27 count. Sorry, you'd be 2 delegates short. I missaid that. 2 delegates short. That's why candidate 2 and candidate 3 get bumped up. They have the 2 largest fractional parts. Okay, so here are the quota deviations here, deviations from quota. So the raw math says that candidate 1 is owed 12.512 delegates. But she only gets 12 delegates. She gets less than her quota, less than what the math says she is owed. And how much less? 0.512. Right? Take your apportionment value minus your quota value. So she gets like roughly half a delegate less than what she is entitled to. On the other hand, candidate 2 gets 7 but was entitled to 6.585. So she gets like an additional 0.415 delegates. Okay, so a positive number over here means you got more than your quota. A negative number means you got less than your quota. So the positive numbers are like the candidates who were treated favorably in this particular setup, right? I mean, these numbers, generally speaking, won't ever be 0. I mean, if your quota was exactly 12 and then you got 12, that's how you get a 0 out of that. So generally speaking, these numbers, though, aren't 0 because that's fairly rare. What I just described is fairly rare. So you're going to get basically like a positive and negative numbers here, and the positive numbers are showing you which candidates were favored in this particular election. Of course, if I jiggled these vote totals, that would create new quotas, which would create new quota deviations. So these numbers, like this number here, is just saying in this particular election, candidate 1 was like disfavored. So anyway, there are the 4 numbers, your apportionment minus your quota. For NIE, the apportionment is 13,752. So if you round these guys like normal, that's what NIE does. It starts by rounding everything like normal. This will get rounded to a 13, a 7, a 5, a 3. If you add up those numbers, you would get 28, which is too many. You've exceeded 27 by 1. So recall that NIE, when you get too many, it reacts by punishing the person at the bottom. So this person gets their 1 taken away from their 3. So you rounded them to 3, and then they get an additional delegate taken away after that to knock to hit our target of 27 delegates. And here are the deviations now. So now candidate 1 is doing well in this election, right? They get roughly half a delegate more than what they're owed. Candidates 2 and 3, their apportionments match, right? 7 and 7 and 5, 5. So their deviations don't change. But now look at poor candidate 3, right? Negative 1.293. So they lost more than a delegate based on what they feel they should be entitled to, right? They should be entitled to 3.293. Now, one thing I want to point out here, and I'll point it out again later when we really need it, if you add up these 4 numbers here, you will get 0. This is a zero-sum game, if you like, right? So candidate 1's gain is like candidates 2, 3, and 4's loss. Everything's balanced here. So if you add up the quota deviations across the candidates in any election, you will get 0 out of that. So it balances at 0. Because again, my gain is your loss. It's a zero-sum game. The SUQ apportionment, recall how that works. You just start at the top and then work your way down and rounding everybody up as you go. So this gets rounded up to 13, up to 7, up to 5. And then by the time you reach candidate 4, there's only 2 delegates left. So in this particular election, the NIE and SUQ apportionments agree. That will happen sometimes. They don't always agree, of course, but in this case they did. And so, of course, if the apportionments are the same, the deviations are the same. So here's an example of, in a given election, right, this is a fixed election, what each candidate's deviation from quota is. Again, how much you got minus how much the math suggests you would get if we didn't have to do any rounding or anything. Okay, so finally, our big definition here. So this project was made to finally get us here. Okay, this is the big punchline here. The asymptotic delegate bias of candidate I. It sounds so fancy, doesn't it? Anytime you use the adjective asymptotic, I feel like something fancy is about to happen. I should say that when I say this out loud, though, I always just call it delegate bias, or sometimes just bias, because it's, I don't know, it's a mouthful to say this whole thing. So anyway, the asymptotic delegate bias of a given candidate, and again, I should re-emphasize here, the candidates are assumed to be ordered by vote total. So C1 is the leader, C2 is the second place candidate, and so on. Okay, so that's important here. You are assuming that there's like a definite leader, and that's C1, and so on. Okay, so what is the asymptotic delegate bias? Well, you have to have a method in mind. So you have an asymptotic delegate bias under Hamilton's method or under NIE or whatever. What is that? It's the candidate's average deviation from quota over many, many elections. Okay, so what does that mean? Here was a single election, and we looked at people's deviations. Some were negative, some were positive, whatever. Now just imagine like jiggling these vote totals or choosing another election at random, something like that, right? And then doing that again. Doing that again. So you're going to choose like billions of elections at random. And every single time you do that, you record a quota deviation. So for just billions upon billions of elections, you sort of throw into a spreadsheet candidate one's quota deviation. So you have a spreadsheet with a billion numbers in it, right? So every time you do an election, you look at the apportionment. So you have a method in mind, right? So NIE is maybe your method. You have a method in mind. So you choose an election at random. You calculate an apportionment. You then see what candidate one's quota deviation is, toss that in a spreadsheet, and then repeat that billions upon billions of times. If you just keep doing that, the asymptotic delegate bias of C1 is the average deviation from quota. So again, you have a spreadsheet filled with numbers like this, and you just take their average, right? Excel has like an average command, right? Just ask it for the average quota deviation over many, many elections. So the asymptotic delegate bias of C1 is the average amount that C1, the leading candidate, receives above her quota. And if you had a negative number, that would mean that on average you receive less than what you sort of should, right? So again, in this example here, candidate 1 received half a delegate less than what she should have on some level, right? She was cheated out of half a delegate. But maybe in other elections, she gets 0.75 more than she should get. So there's a positive 0.75. And then the next election is negative 0.8. The next election is positive 0.3. The next election is negative 0.2, whatever. Right? You keep doing this over and over and over again. It's not clear what would happen, but if in the aggregate, the overall average was bigger than 0, then you would say that Hamilton's method sort of favors candidate 1. But if it came out negative, right, in the aggregate, you would say Hamilton's method is biased against candidate 1. If it averaged out to 0, you would say it's neither biased against nor for candidate 1. That's the kind of information that you're learning here. Okay, so notice this word here, average. Okay, now as I'll show you in the final video of this stuff, deviation from quota is a function. So you're doing the average value of a function. So in the end, we're going to calculate, go all the way back, we're going to calculate like this, right? The average value of a function is like this. You have to divide by the area of some region, we'll talk about that next time, and do an integral. So all that to say, sorry about all this, asymptotic delegate bias is calculated using a double integral. So the question is, how do you calculate it? Again, I'll show you this in the next video. I'm going to terminate things here to try to keep these videos short. I know I keep saying that. Again, usually this is like 2 class days of discussion and stuff, right? So I'm trying to do it all in a video. It sort of takes a while. But anyway, how do you calculate the asymptotic delegate bias for a given candidate? Again, you have to have a method in mind, right? So under Hamilton's method, how would you calculate for candidate 1 their asymptotic delegate bias? What you do is you take a typical shape of the method, and we've talked about this before, right? Hamilton's method, I'm talking about a hexagon. So take your favorite hexagon from the Hamilton triangle and look at it, right? And for NIE, we're talking about that arrow thing. And for SUQ, we're talking about a diamond. So when I say typical shape, I'm saying get away from the boundary where things are distorted. I'm not talking about the half hexagons or whatever. Go inside, take a typical shape. Recall that the actual picture here, right? These pictures, I've drawn them on the screen, of course, right? These are flat, but we saw that these are actually floating in 3 space. So it's a 2-dimensional thing, but it's slanted in 3 space. So before you integrate over it, you have to shove it down to the floor. So you shove it down to the floor, the XY plane. Then once it's sitting in the floor, you can calculate a double integral over it. Okay, so double integrals assume a region in the floor. So again, this first step is necessary to set up a double integral. You then calculate the double integral of the quota deviation function, right? Average deviation from quota. So again, I'll show you how to build this function in the next video, the final video. But there's a function there. You calculate the double integral and then divide by the area of the region, creating an average value, right? Integrate and then divide by the area. So, punchline, because delegate bias is an average value of a function, the function being deviation from quota, which I'll show you in the next video, you calculate it using a double integral and then dividing by the area, but a double integral, and thus, okay, and thus, studying the bias of these methods is an application of chapter 15 of your textbook. Okay, so again, the big question here is like Hamilton's method. Does it favor the leading candidate or not? Does it favor or punish the bottom candidate or not? How would you answer a question like that? The answer is chapter 15. So you figure out a deviation from quota function and then take an integral and divide by an area, but mainly take an integral. And then you'll learn if a given method is favoring or disfavoring a particular candidate. And again, like, it's not totally clear if Hamilton's method is biased towards the leader or not. It doesn't seem like it is based on the rule description, but it'd be nice to know. NIE is clearly favoring the top candidate. Based on the rule description, it's clear that NIE is favoring the top candidate and punishing the bottom candidate. But you can still ask, how much? How much is NIE biasing towards the first candidate? Is it more than SUQ, which also clearly biases the first candidate, or is it less? If less, by how much less? So again, this asymptotic delegate bias, it's a way of quantifying how much bias there is in favor or disfavor of a given candidate. And this is useful information to know if you're, say, a state party official trying to decide what kind of method to use to apportion your state's delegates in the presidential primary. Like, how much do you want to bias the top candidate? How much do you want to bias against the bottom candidate? This metric here, this measure of bias, can sort of quantify that for you and help you make that decision. Okay, so in the next and final video, I'll show you how to actually do this. But again, it's very nice that a double integral will quantify for you the amount of bias of an apportionment method in favor or disfavor of a given candidate, which again is very useful information that you might want to know if you're choosing an apportionment method. Okay, so in the final video, I'll show you a couple examples like this, and then we'll be done with these videos.